When a nuclear power plant is shut down or an accident occurs, there's a continuous need to cool the fuel because there's a lot of residual heat that comes out of the fuel due to the radioactivity. So where you have loss of a coolant, you have a potential for a serious accident, and that's effectively what happened at Fukushima. The earthquake triggered a shutdown of the reactors, which was appropriate and went flawlessly as far as we can tell, but the tsunami caused the loss of coolant. And so even after you shut down a reactor, you have to maintain coolant for literally months, otherwise you have the potential for an accident. At Fukushima, the coolant was lost, and the cores of 3 of the reactors were extensively damaged. In one case, they probably pretty much entirely melted, flowed to the bottom of the reactor vessel. And what you end up with is something very different from what you started with. You start with a well-defined fuel in a cladding in a reactor that's behaving normally, and you end up with a very inhomogeneous agglomeration of fuel and other components of the reactor that have all been melted and accumulated together at the bottom of this reactor core. And then at Fukushima, in order to cool the reactors in an emergency situation, the decision was made to pump a lot of seawater in. The issue there is that your seawater is then interacting with this bizarre material at the bottom of the reactor vessel. It has the potential to dissolve a lot of radionuclides and transport them out. And that's exactly what happened in Fukushima. The paper is focused on that actual process. How the seawater or other water, doesn't have to be seawater, but how it interacts with the actual fuel that's been extensively damaged in the accident. What processes are determining what radioactivity is released and how it's released and how fast it's released is what we're after. And a major point of the paper is that we don't have sufficient knowledge about that process, or those many processes actually that would be occurring. In particular, we have very little means of predicting what release rates of radionuclides from such a material would be in water, and as such we don't have any way to guide the response teams.